Hey, good morning, everyone. I'm Silja Renooij. I'm from the Netherlands and Utrecht University. And I'm a researcher in probabilistic graphical models. And this morning, I would like to give you an introduction to probabilistic models. And I could be sharing stuff that some of you may know or you may not know, but the idea is that after this morning, everyone is basically on the same page, and you all know what's, or are prepared for what's coming after. So it's to basically ease you into the topic, and then afterwards you'll be working much harder than this morning. So as I said, I'm Silja Renooij, and actually the plan was that I was to be sharing this presentation this morning with Antonio Salmeron, but he couldn't make it. He did share his material, so I'm very grateful for that. So you'll have to deal with me alone this morning. So if we talk about probabilistic models, probabilistic AI, when I think back to the 1990s, when there was Deep Blue, the chess machine that beat the world chess champion at that moment, I remember because it was in the news everywhere, because at that stage that was, wow, this is what AI can do. But if you think about how much effort they put into back then, compared to what AlphaZero did a couple of years ago, starting from scratch, learning chess in 4 hours, and being very, very good at it. So actually the quote here is from a BBC interview with Peter Heine Nielsen. So any Danish people here and also Norwegian people here. He is a chess grandmaster and also the coach of Magnus Carlsen. And he said, well, I always wondered how it would be if a superior species landed on Earth and showed us how they played chess. Now I know it. But the question is, do we really? I mean, if you think back at Deep Blue, basically there was some knowledge and rules about how to play chess that was used to train the system. And here there was nothing there, right? So does it really know how to play chess? Well, apparently, because it does. Could we learn something from it? Probably not, because we don't really understand what the system is doing. So if we really want to learn ourselves how to play chess from such a system, we should be able to understand what it does. So can we learn anything from it? Probably with these kind of black box systems, we can't. So that is a reason, and it's becoming more and more important, and maybe not for chess, because we don't really care if something is good at playing chess or not. It's not, well, it's not critical that a system is good at playing chess. But if we use such systems, for example, in the medical domain or in the court of law, then it becomes really, really important that we know what it's doing. So we should be able to interpret that and understand what it does. And that's the reason why going to types of models that are more interpretable than the black box systems we have. So just to give you a couple of examples, again, this one is especially for Antonio, who isn't here. A region in Spain where he's from, and this is an example where they're using models to determine how land is used in the region. So you can predict from satellite images, for example, the land use. You can also generate from what the data that you have new data to look at what the land use is in parts where you don't have any data. And this is used to monitor protected areas. Another example, this is, well, where we're looking at, 80 years after D-Day quite recently. This is a grave of an unknown soldier, not on any of the Normandy beaches, but this is actually in a cemetery in the Netherlands, where there are lots of English soldiers who took part in Operation Overlord, part of Market Garden operation, to liberate the Netherlands. And, well, there's still many, many soldiers unknown soldiers in graves. And what they're trying to do is determine who these boys, often young boys, were. So they have DNA from relatives, possibly faraway relatives, and they're now trying to find out if they can find matches still between these unknown soldiers and relatives still looking for their lost relatives. And in general, for all sorts of disaster victims, there are systems being used to try to match people that were the victim of a disaster with their relatives using large sets of DNA profiles. So there's actually a Dutch system, Bonaparte, that is doing this. This is a typical example, the self-driving cars, using all kinds of sensors and whatever to be able to move around, to decide when to accelerate, when to turn, when to brake, and of course trying to predict crashing into things. And the nice thing about using probabilistic models in doing that is that you can take into the risk into account explicitly when you are making decisions. So you also know what the cost is if you neglect a certain probability that you will hit something, and you can try to avoid that. Then finally, when we talk about generative AI, which of course everyone is thinking about, we started with text and ChatGPT, and now we can generate images from text and music and whatever. Who's been playing around with stuff like that? Who's been using ChatGPT? Anything else? Who's been generating music? Some images? Few videos? Not many videos yet. Good, then I have something new for you. So I started playing around with this too. So I thought, okay, I can now use just a text prompt and generate a video. Let's see what it does. So I gave it this very simple prompt, didn't think a lot about it, just said, okay, give me a video on the fun and use of a summer school on probabilistic AI in Copenhagen. And this may officially not be called a summer school, but well, it's summer, isn't it? So I just gave it this, and then I looked what it came up with. Let's see if I can show that to you. And this was all I gave it, so I didn't even tell it was supposed to be a promo video. I didn't edit it in any way, apart that I said it should be in landscape, because it was going to make a YouTube short, so it was in portrait mode. And you see all it's telling you where it was has taken images, so if you pay for it, you can get rid of that too. But so this is just from this simple text prompt and nothing else. Okay, so I think the video gave motivation enough for the rest of the course here today. So let's move from examples to more contents. So what have we seen in all these examples? Or maybe you haven't seen it, but what is underneath? So all these examples, we are dealing with situations where we have large amounts of data that we have to process. But there are also such complex domains, complex environments that no matter how many data you have, there are also a lot of things that you don't see and will never see. So you're never covering all possible things that are out there and that you may want to model or reason about or predict or whatever. So there's always uncertainty. And a lot of these things use probabilistic models to learn from the data, and inference algorithms to compute predictions, for example, and also to look at how the domains are structured. So what variables are related to what others, and stuff like that. And the nice thing about probabilistic models, especially compared to the more black box things, is that we have a way of quantifying uncertainty that is more or less accepted because we just have probability theory, and using probabilities means we have all the rules and all the math available as tools to operate with it. It also gives us a natural way of dealing with missing data. And then, I mean, more in general, if you think of tabular data, not just missing cells, but also missing entire variables, so entire columns, basically, we will see many situations, many examples this week of where you can easily deal with that. And they offer the interpretability, which was basically the chess example that we didn't have. Okay, so uncertainty. Often we distinguish between two types of uncertainty. The epistemic uncertainty, which is typically a lack of knowledge, and the aleatoric uncertainty, which is just due to randomness that you have anyway. Right, so if you look at an example, you've got two variables, x and y, and you've got data with observations of both of them. So, for example, y could be the production of yeast that you're growing, x could be the temperature at which you're exposing. So you have these observations of combinations of temperature and yeast growth within, let's say, 24 hours or something. So you have all these observations. So what you can do is estimate a joint distribution on all these observations, and then use that to predict what the yeast growth will be given a certain temperature. So you can use the definition of the conditional probability there, the probability of y given x, and divide your joint probability by the probability of x. So if we first start with the joint distribution, what kind of uncertainty do you have in that distribution? So if you have all these pairs of observations and you want to estimate the distribution from that, what kind of uncertainty is in there? The first one. The second one, okay. Does everyone agree with the second one? Is there also the first one? If you estimate the joint distribution from pairs of examples, what kind of uncertainty is in there? Epistemic, aleatoric, so we both have both. And you say it's both, okay. Yeah, well, indeed, it's going, in the end, we have both. Can we fix the uncertainty that's in there? Get rid of it? No. Yeah, so to get rid of an epistemic uncertainty, you would need infinite number of examples. And would you then also get rid of any aleatoric uncertainty? Okay, so if we have more than enough data, infinite amount of data, we could say, okay, then we have epistemic uncertainty in the joint distribution, and we could get rid of that. But if we look at the prediction, and that's what we in the end want to do, so we want to predict y from x. And my claim is then you are always left with uncertainty there. Right? Because what is the answer you're getting? If I say, okay, I have this x, the temperature is 25 degrees. What is the yeast growth going to be over 24 hours? What kind of an answer do I get if I'm using this model? And I'm not asking for well, it should be I don't know, 2 centimeters or something, but so what kind of answer do I get? Do I get a number?
You might get a number, but also you might also be interested in quantifying how much variability you expect around that number.
Yeah, so I get a number, but that number is a probability, right? Not a value of y. Yeah. And I could say, well, I'll just pick the most likely one, and then that is my value of y. But there's still, I get a probability, so there's still uncertainty. So no matter how accurate my joint distribution is going to be, so if I get rid of all the epistemic uncertainty in how I'm going to use it, and the predictions I do with it, so anything I compute from it, there's still going to be uncertainty there, which I won't get rid of. So we have the reducible uncertainty, which, for example, by gathering more and more data, we can get rid of or try to get rid of as much as possible. But we also have irreducible. So if we're using the models, no matter how accurate the joint distribution is going to be, we do predictions and we get a probability distribution. So there is uncertainty there. Okay, so we said one of the ways of getting rid of uncertainty is gathering more data. There are also other ways, and this is a very simple example where, let's say here you have a number of observations of 2 different classes. The one are the green X's and the other are the red dots. And you see, no matter how much data I would get there, there's an overlap between the 2. So I can never separate them just by gathering more data. And that is because here underneath, it's actually not 1-dimensional, but 2-dimensional data. So if I introduce the 2nd dimension, and of course this was generated the other way around, but if I introduce the 2nd dimension, then I can see that I can actually separate the 2 classes. And sometimes this sounds a bit counterintuitive because I'm increasing the complexity of my model, but yet that makes it easier to distinguish the 2 cases. Okay, so it's generating more data doesn't always make the problem easier, or gathering more data doesn't always make the problem easier to solve. In this case, you could also get rid of the uncertainty by introducing another feature. Okay. So I've been talking about probabilistic models, and now I want to go from there to a class of probabilistic models we call probabilistic graphical models. Anyone already familiar with probabilistic graphical models? Anyone who's not familiar with, maybe that's an easier one. Okay, a lot of people not familiar, okay. Anyone heard of Bayesian networks? Yes, well then you have seen probabilistic graphical models. Okay, so Bayesian networks are one of the examples of very basic, what I see as the simplest probabilistic graphical model. Not everyone would agree with that. But the nice thing about the probabilistic graphical models, well, they're probabilistic models. They can deal with high-dimensional spaces. So we just saw the example where it is beneficial to add a dimension because it makes the problem easier to solve. But then you also need models that can deal with this high-dimensional data. Probabilistic models also, because of the math, they're giving you algorithms for and support for inference and learning. And the nice thing about probabilistic graphical models is that they have this graph that gives you an interpretation of how variables are related to one another, and therefore gives you an intuition about what the space looks like, and also gives you the possibility to basically construct the high-dimensional model in terms of small local models. And we will see, so if you know Bayesian networks, you know what I'm talking about, but if you don't know them, we'll see some examples in a minute. And the benefits of those all is that you get relatively efficient inference and learning that take this structure into account. And we have something, the graph structure, which is, but you can argue about this, interpretable by humans. Okay. So if we're looking at probabilistic models, I said I will give you some examples in a minute, but let's first go through what we call the probabilistic modeling cycle. And what we start off first is with building a model. So basically we choose what kind of model we're going to use. So we hypothesize that this is the model that is modeling our domain. And then what we can do is perform inference, so compute from our model the things that we're interested in, validate or criticize the model, see if it's doing what we expect it to do, fine-tune it, so go back and revise the model if we need to, and repeat that process until we're satisfied that it does what it's supposed to do, and then we can apply it. And if we think about this, then what we're looking at in terms of where are we using the PGMs is that, so what we're going to look at is we're assuming that the model we're hypothesizing is a probabilistic graphical model or can be represented as a probabilistic graphical model. So actually a lot of the standard probabilistic models can be represented as a probabilistic graphical model. And the one I wanted to focus on a bit more is the Bayesian network. So we have the definition here in a small toy example. So the definition is a Bayesian network is over a set of random variables, so it's a high dimensional. In this case, I'm assuming n variables. So we have this graph structure, which is a directed acyclic graph. Every node in the graph represents one of the random variables. And we see these local distributions. These are all tables if we assume the variables to be discrete. We do not necessarily have to assume that. So these could also be continuous distributions. In this case, they're discrete, so we have simple tables that represent those local distributions. And you see they're nice and small. So every node or every variable has a local distribution for its own values conditioned on the values of its parents. And in this example, even all the variables are binary valued, so we only have true and false. So, and you see that this gives you these nice small tables. The true and false here is so we've got two values of the parent alarm being true, alarm being false, and these are the probabilities of Mary calling being true. So the complements, probabilities of Mary calling being false are not even shown there, but they're 1 minus these. Okay. So this specifies a complete probabilistic model over all these variables. And you see that it's a directed graph. So does anyone know what the arcs mean? Some of you have seen Bayesian networks before. It's what, sorry? Yeah, so they indicate which variables depend on which other variables. Any other interpretations? Yeah, they at least, well, as I said, people claim that these graphs are intuitive, right? So if we see arrows, we tend to interpret these as causal relations. If you look at this example, you could also interpret them this way, right? So the burglary causes the burglar alarm to go off. An earthquake may cause it to go off. And if the alarm goes off, then either John calls or Mary calls or both call. They're not necessarily causal They do not necessarily have a causal interpretation. Sometimes you can just reverse the direction of the arcs and it doesn't really change the meaning in the mathematical sense, but it will if you look at the graph as a human being and say, okay, if the arc is against a causal direction where a causal direction is possible, then it starts to get confusing because it's counterintuitive. But mathematically, it could have been the same model. Not in this case, by the way. If I change one arc direction, then I'm having something different. But that was a very simple, small example. We can go to larger models. This is an example of a real-world network. You could still call this small, but for a realistic model that does quite simple diagnosis. These are all discrete variables, in this case of classical swine fever in pigs. Then these types of networks, then this is quite a size that you see quite often. So these are not these really huge models that you can see in all the when you work with images or whatever. So this is a simple diagnostic system that tries to detect whether pigs suffer from classical swine fever. And you see, well, then it starts to become messy already. So the nice intuitive graph representation starts not to be very helpful anymore. But, well, there's still some things you can see there. What you also see here, so there's some main diagnostic variable, which is the, I think in this case, you see the CSF right there, which tells you whether or not the pig has a classical swine fever, and it's a disease that goes through a number of phases, where the phase 5, they're very clearly visible that the pig has the disease. But you basically want to detect it already when it's in phase 1, because it's very, very contagious. So they want, if there's an animal that has that, they want to make sure that the animal is killed, and even the whole farms, all the animals are killed off. But you should prevent from transporting these pigs to other places because it will spread very rapidly. So here they want to diagnose that very early. So there's a couple of variables in there that you will never observe directly. Right, so basically these are, if you think about gathering data, you will never have data of these. And there are other variables where you do, but still you can build such models. This one was constructed completely by hand, without data. The data that was there was used for verification purposes. And also the data that was there was only for healthy pigs, because when the model was constructed, there was no swine fever. So that's also a problem with gathering data. You cannot always have the data that you need, right? But, well, in this case, as I said, this was a hand built, but you could use knowledge, you could use data, you could use combinations of the two. Okay, so a little more about the interpretation. You can see the big graph as being constructed from smaller building blocks. And these small building blocks, if you think in terms of connections of 3 or more nodes, they have an interpretation. And as I said, if we can give it a causal interpretation, that's nice. But from a mathematical point of view, what the graph basically represents is an independence relation. So it captures probabilistic independences. And it does that through what we call deseparation. So if variables are deseparated in the graph, they are independent in the distribution. And we distinguish 3 different cases where if we have a serial connection, we say that if we look at a chain of 3 nodes, then this chain is active unless I observe one of the nodes. And the observation for a node is where the node is given a yellowish color in this case. So if there's an observation in the top one for B, then basically information cannot go back and forth between A and C, but it's blocked at B. If B is not observed, we can't pass on the information. That means if I do something at A, it will affect C, and the other way around. Also the other way around, against the direction of the arc. And that means that in the second case, A and C are the chain between A and C is blocked by B. I was about to say A and C are deseparated by B, but that is only if all possible chains between the two are blocked. So if you look at a big graph, and you look at all possible chains between two nodes, and you look at are there any observations there, or different structures that make me conclude different things, and you want to know, are these deseparated, and if they are, they're independent. Okay, so the first two situations are very similar. So if we have a serial connection, or we have a divergent connection, and I've got 4 nodes in the picture, but 3 would be enough as well, then they work the same way. So if there's no evidence, no observations, the chains are active. If I put evidence in there and I say, okay, now I know the value of this variable, then the chain is blocked. The third one, it's the opposite. And that is if I have 2 or more incoming arcs for a node, then the reasoning is completely the opposite. So these chains are blocked if there is no evidence for the node in the middle. So just the fact that there is a chain with a head-to-head node already blocks the chain. And to make it a bit more complex, it not only holds for B, but also for any of its descendants. So if I do have an observation for B, or any of its descendants, so basically that would count as an indirect observation for the node, then suddenly the chain is opened up. So the easiest way to remember is just to remember the first 2, how it works. So no evidence means active chain. Evidence blocks the chain. You can visually see that there's something there. And remember that whenever there are 2 or more incoming arcs for a node, it works the other way around. And this tells you how to read from a graph the independences among the variables that you're modeling. So even if you have a huge graph, you could tell what kind of dependencies are there. And if I start entering evidence into my model, how these change. Because you see that dependencies, things that are independent can become dependent and the other way around. So this gives you a language. Basically, the graph is a language of telling you, okay, what are the independences that we have in our model. So for who of you is this the first time you see deseparation? A few, okay. Who has seen deseparation but thinks they still don't quite understand it? Okay, let's see if we can change that. So I have a simple example here, and you see it's more complex than the simple alarm example because indeed we now have loops. So we're talking about acyclic graphs, but that means just if we follow the direction of the arcs, we cannot go around in circles, but we can have these kind of loops here. And you see you can go around following the direction of the arcs. So in this case, I have variable A. And so that is just call it A because that was where I wanted to start. And B and C have evidence. So they are the same rule as I just showed you before. So which variables in this graph are deseparated from A given the evidence, the observations for B and C? D and F, E and F. Okay. Anyone with a different answer or more? Only F? see if I can put this on the board. So I've heard E and F. I've heard only F. Anyone else? H. Oh, you're just now going to call all the letters. Well, let's see if we can figure out how this works. So if we go from A, we cannot go through C, right? Because C is blocking the chain right there. So we cannot go to the left. Can we go to the right? Yeah, we can go to D. So D cannot be D-separated because we can go there. Well, none of you said D, so that's good. Can we go up to B? Yeah, we can go up, but then it's blocked, so that doesn't do anything. So we go down from D to E. That works, right? Yeah, so E is not D-separated. Can we go from E to G? Yeah. From E to H? Yeah. Okay, so H is not D-separated either. Okay, can we go back up? No, because that's the head-to-head, and we don't have evidence for H. So we can go down to D, E, G, we can go to H, and then it stops. So only F is D-separated. So what we find here, green is where we can go, and everything outside of that, we cannot.
How would it be different if we were to observe only F in one case and only H in another?
If we observe only F, so we have, it's a good thing I have a blackboard here. So this situation, right? We only have evidence for F? Oh, that's that one.
And from D to
From B to... Oh, yeah, D to E. Yeah, that one. Yeah. Okay, and this is the only evidence you have. And I'm starting from A.
yeah, we are starting from
Yeah. Okay, so now, so I can go to C, E, H, and G, right? I think everyone could agree with that. I can go to D. Okay, can I go up to B? No. Okay. When I'm here, from E to H, can I go up to F? No. Does that answer your question?
I mean, in the sense that if I observe only F over here, then I can say something what B would be, but I cannot say anything else besides B.
No, you can, so in this case, A is D-separated from B because you could never reach B. And you can reach all the other ones.
Even if F is a parent of H, I could still reach H.
Yeah, but if you do it like this, if I only put evidence on H, then I'm opening up this chain, and then I can go back up. So then I could reach everything. Yeah? Any more questions? One other example? This one. And, well, what you see here that I have evidence on M, which is a child of a head-to-head node. So that is basically opening up that chain from H at HKI. And what we see here is these are the nodes we can all reach. So indeed HKI is opened up. We can go to the top there. We can go to the bottom, but here for this head-to-head node L, it doesn't have evidence. It has no children that can have evidence, so there it stops. Okay, so this is how you can determine from the graph which nodes are independent and which are not. Yeah.
It's a good time to ask, would probably find that this one draw?
Practically. Well, it can tell you, but basically, the graph gives you the language to represent independences. Where we exploit those independences is exactly here in this formula. Because of the way we do this, this means that all the local models that I said, so we have the local distributions for every node given the parents, that those, if we just multiply them, gives us the joint distribution. And that is using exactly the independences that are coded in the graph. So they're used indirectly there. So I can write the joint as a factorization of these local models because this is what the graph means. And that's where the d-separation is used.
I would think that you could write that factorization just by looking at the arrows without
Well, if I put, for example, evidence here, it means I'm going to compute probabilities conditioned on this evidence from that formula. So still I'm using that. Maybe not consciously, but I'm still using those independence properties. Right? So the only reason that I can write it in terms of local distributions in the graph is because this is what the graph encodes through d-separation. Of course, you can say if I know the factorization, I don't need to draw the graph. But it defines, in that sense, it also defines the graph. Right? So either I have the graph and I know what the factorization looks like, or I have the factorization and I know what the graph looks like. So here's, again, a simple example that shows you how to factorize a joint distribution over all the local probabilities, like that. Another nice thing is that you can easily use these building blocks to extend your graph. Because all those models are local, if you make a change to the graph, if you add a variable, you only have to look at, okay, where does this change my local distributions? So in this case here, if I add to this simple model about predicting whether or not there's a forest fire, so there were temperature sensors and smoke sensors, and now I add two different variables. One with this says there was a cigarette found, and the other was the season. Then the only thing that changes is that the temperature variable gets an additional parent. So that means in the local distribution, I have to add a variable. And that's the one right here. So the temperature now has two parents, the season and the fire. And also I added the cigarette. So smoke gets an additional parent right here. So smoke has fire and cigarette. And I added an additional sensor as one of the children, which gets its own local model conditioned on smoke. So that's the one here. See, there's a conditioning bar. Oh no, this is the prior for season, sorry. This is prior for cigarette that was added, the two on top. And here we've got the probability of the sensor, the second sensor for smoke. So you only have to change local things, and that's also nice. Okay. So I wanted to give you an exercise that you can do, which is a very famous exercise, but there's always a lot of discussion, even among statisticians, about this. And let's see if we can figure out why that discussion is there. See if we can have a similar one. So the problem is the Monty Hall problem. I think most of you will have heard of that. Who hasn't? It's also known as quiz door problem, things like that. Okay, so the problem is you're in this game show, and you're a contestant, and there are these three doors, and behind one of the doors there's this big prize that you want to have. It used to be a car, I guess, but you can think of any other prize you would like to have if you don't want a car. And the other two, well, there's something behind that, but not really something you want. The typical example that there's a goat behind those doors. So maybe you would want to have a goat, and then you think of something else you don't want to have. So the idea is you as a contestant get to pick a door. And you go stand in front of the door. And then the host, Monty Hall, is going to open one of the 3 doors, show you what's behind it, and then give you the option to swap, to switch doors. And the question is, would you do that? Okay, so if we try to model this, and then basically we have 3 variables, right? We have your choice of door. So this could be door 1, 2, or 3. That's variable C. We have the door that is opened by the host. Again, this could be door 1, door 2, door 3. That's variable H. And we have the door behind which the real price is, which could also be door 1, door 2, or door 3. So I just gave you 4 different possibilities of graphs over these 3 variables. There are much more possibilities than just these 4. So the question is, if you have these 3 variables, what should the graph look like that represents the dependencies between these variables? Because first you need the graph, and then you know what kind of local models you need. Or if it's easier for you to think in local models, it tells you what the graph should look like. Yeah.
I think it should be model 6, because basically your choice of door, when it excludes that door from being opened by the host, so there is a connection or dependency, and also the real price door also represents the open door because the host won't open the door to real price.
Okay. Did I tell you those assumptions? You're making assumptions.
I think the second one not, but that is kind of the same, because if the host opens the door after twice behind it, then the game will be over.
Yeah, so it would be really much fun, right? Yeah. Well, I consciously didn't mention any of these assumptions, so it's nice to see that you're assuming them. At least you're now making them explicit. Because indeed, it's these kind of assumptions that is going to tell you which of these structures is the one you should take. Right? If everyone is just making a random choice, if you as a contestant make a random choice, the host has no clue where the price is. It could even just open the door you picked, and the price is behind any door, then the first would probably be the best representation. But you're also already making a lot of assumptions. So as I said, I've got 4 examples here, but well, you could try and use any graph you would like. I have a notebook for you that you can play along with. It uses this structure, but again, I was making some assumptions that maybe you do not agree with. So in the notebook that you can find here in the GitHub, if you, as Andres said, if you go to well, you can either go to this link directly, but you also can reach the GitHub through the web page. I think I can show you. I can show you. Yeah. So if you're at the school web page, here in your top right corner, you can click on that. And then scroll, then the Nordic ProbAI 2024, right here. And then you go to, so here, day 1 is my presentation, Introduction to Probabilistic Models. There's a materials. And then it's the Monty Hall collab. So the idea is that there's a notebook here that you can go through. As I said, I implemented the structure that contained 2 arrows, the 4th structure. I also put in some probabilities. So figure out what my assumptions were there. And if you don't agree with them, feel free to make changes. And what you can do is also perform some inference in there. Is everyone familiar with how this works, or is everyone maybe with your neighbor capable of getting this to run. And let's say you can start and try to get this running and analyze and play around with it. And then at 1:15, there will be coffee outside, so feel free to have a break then and continue playing with that for a while. Okay, I hope that in addition to coffee and fruit, you got a chance to play around with the notebooks for a while. Is there anyone who would like to share whether or not they would switch? Would you switch? Yeah, you would. Anyone who wouldn't switch? Okay. If you looked at the implementation, then as I said, I chose this structure, but again, I'm making assumptions that you may not agree with. So would you all have constructed the same graph, or do you have reasons to deviate from it? As I said before, right, if everything is a completely random choice, then you would just pick the top left one and there would be no dependencies. And this seems like a reasonable assumption. So whatever choice I make affects what the host does. And if the host knows where the real price is, that would also affect the choice of the host. So this our arc here assumes that the host actually knows which door has the real price, which is not necessarily the case, right? So also that is an assumption that we're making basically explicit by modeling the graph like this. So if you went through the whole notebook, you also did some inference to support your decision of whether or not to switch. And here I've got a number of examples. So what you could do if you have the complete model is, for example, compute the prior distribution over the choice of the host. So you haven't made a choice yet, and we're in a situation where anything can still happen, and you can compute, okay, what is the probability that the host will pick one of the doors? So what we do is we look at the joint distribution. So we have the factorization over the graph. So the variable with the host's choice depends on your choice and the door which contains the real price. Those two just have a prior distribution, and we multiply them. And if we're not interested in your choice or the real price, we sum them out. And then we're left with only the distribution over the host. And in this case, you see, because of the assumptions I put in, that everything is uniformly distributed. So every door has a probability of 1/3, right? Which seems reasonable. And what I did here on the right is say, okay, suppose I have picked door 1. So my choice is door 1. And suppose the host has opened door 3. What is the distribution over the doors for the real price? So where is the real price most likely to be? And I can compute that using Bayes' rule. That's what we're doing here. And actually what we're doing is now reasoning against the direction of the arc. Right? I've got evidence for the host, so that is opening up that head-to-head connection. So my choice and the host's choice are both, well, not affecting where the real price is, but the information is taken into account to determine where the real price could be. And you see that the second door now has the highest probability of containing the real price. And the reason behind that is that in my specification of the local models, I assume that the host knows where the real price is and also doesn't open that door. So that means if you didn't choose the real price, the host only has one door he can open, and thereby he's giving away information. And that's why the probability increases from 1/3 to 2/3. If you discuss and don't agree with all those assumptions, then things may be differently. And they may be so much differently that this distribution stays uniform. Right? And that is basically where all the discussions about should you switch or not come from. So I'm not that much interested in what is the best decision, but what are all the underlying assumptions that you're basing your decision on? And it's nice that you can make them explicit both in your structure and in your probabilities, so you can see that. Okay, so through this example, we've seen a number of things. We have a joint distribution, which factorizes over all those local distributions. And we can compute from that what we call the prior distributions of any of the variables, or the posterior distributions of those variables, given observations for other variables. And the use of these terms is a bit confusing, because if I have a complete model and I'm just, all the parameters, all the probabilities are there, I'm just computing things from the joint distribution over my random variables, then I'm using prior and posterior in this way. When we move to learning, which we'll do in a second, then usually I mean something very specific with that. So here, I'm talking about prior, I could be the prior of any of these variables right here. When I talk about learning, if I use the word prior, I'm typically interested in the parameters and not, let's say, the domain variables right here. So that is something to keep in mind. So computing probabilities from such a Bayesian network or probabilistic graphical model or probabilistic model in any case is what we call inference. So what we did here is we had a Bayesian network, we had some variable of interest. For example, which door contains the real price? And we can compute the posterior distribution over some variable of interest given the evidence that we have, which could be nothing, or any set of observations for a subset of variables. And we typically distinguish between exact inference algorithms and approximate inference, where you would like to do exact if you can, and sometimes we need to do approximate. And exact inference you could do in a brute force way, right? We know that the factorization specifies a joint distribution, so we could just compute the whole joint and then sum out everything we don't need. But that's not the most efficient approach and quite infeasible usually. But we can benefit from the structure, so we can benefit from the fact that we have this factorization to do this in a more feasible way. And if we still can't do it then we have to resort to approximate inference, and basically you can distinguish between two types of approximate inference. Ones are sampling based, like MCMC, and the other ones are more deterministic in the sense that you first approximate your model into something that you can do exact inference on, and then basically do your exact inference on that. And we'll see a lot of that in the remainder of this course, especially the deterministic one. Okay, just to give you a very simple idea, or a very brief idea of how exact inference could work. This is an algorithm called variable elimination, and in this case, suppose I'm interested in the distribution over x5. You see it's conditioned on some parent, so I don't have that available already. So I need to compute it from the joint distribution by summing out all the variables that I'm not interested in. So what you see in the first row there, the first line just gives you the joint, and then I want to sum out all other variables, x1, x2, x3, x4. So that's the same thing as summing it out from the factorization. And where I can exploit basically the structure is that I don't have to compute the joint first and then sum out. But if I'm a bit smart, I can try to push some of the summations as far as possible into the product. And here, for example, I can push the summation over x1 all the way here. and I only have to include 3 of those local distributions, sum out x1, and that gives me some other function, which may or may not be a probability distribution. And I repeat that until I get some product of other local functions that gives me my that solves my problem for me. So basically, you repeat the same process over and over again with 1 or more variables less. And that's the idea behind variable elimination. Okay, so we were looking at probabilistic graphical models. We have seen that we can represent them using a graph structure that basically defines the factorization of the joint. So that means we have these small local models that we can use to represent the joint distribution and thereby compute basically any probability that we want from them. We have seen that the nice thing about the graphical representation that it is, at least in some sense, interpretable for humans. If you really want to interpret them in the right way, you need to understand deseparation, which, as I said, that is the real interpretation. If you start to see it as causal relations, sometimes you may go wrong. So you can argue about the true interpretability of the graph. And we have seen that, well, I've shown you a very simple example, but we have algorithms that can do inference, and we can also use them to do learning. So inference was computing probabilities, and I want to show you that, in fact, there's not much, well, there's very little difference between inference and learning. And that's more or less the remainder of what I'm going to show you. So when I talk about learning, I could be talking about learning the complete model. So that means both structure and the probabilities. But in this case, learning structure is beyond the scope of what we're talking about here. So I'm assuming we have the structure. So you use your knowledge of the domain to construct the structure. And I'm only interested in learning all the parameters from the data. And with parameters, I basically mean the things that specify the distributions. So in this case, I have discrete variables. So I need the numbers in the probability tables. Those would be my parameters. But if I have continuous distributions, if I, for example, have a Gaussian, then my parameters would be the mean and the variance. So back to the probabilistic modeling cycle, because we didn't have data in the previous image, and it should be there. Actually, I took it out from the original image, so this is the original image. And the data is entering into the process where we talked about inference. So inference is about computing probabilities from your model. And we can use the data there to actually learn the parameters of our model. Those are just, can just be represented as variables, and we have the mathematical tools to compute probability distributions over them. So we use the data, on the one hand, in the construction phase to establish the parameters. I'll say more about that later. On the other hand, you can also, of course, use it to criticize and validate your model, and you just continue that until you're satisfied. So again, the model you could be considering could be any kind of model that you, any kind of probabilistic model. The type of quantities you want to infer, there are different types of inference algorithms that you could use, like MCMC or variational inference. And in the end, you want to have a model that you could use to do your predictions or to generate data or stuff like that. So we're talking about learning. And nowadays, usually if you say, okay, machine learning, everyone knows that this is something you can do and has an idea of what it means. This is a definition in the 1997. You had to give a definition of what machine learning was. So we just took the definition here. And it says a computer program P learns from experience E with respect to some class of task T and a performance measure R if its performance on those tasks measured in terms of your performance measure improves with the experience. So basically, you should get better the more experience you get. That's the definition of learning. So let's look at a very simple example. If you look at a lot of the literature, often this is one of the simplest or first example models that you try to use. So I'm looking at two variables, x and y. I have some data about that. So the data is our experience, right? We've seen this. And we want to predict the value of y from the value of x. So let's say we just pick a linear regression model. So it looks like this. So we approximate y by through a linear function of x. And if we want to construct this model, what we need to establish from the data is what is the a and b. So what is the slope and what is the offset? And to see how good the fit is, we can use the root mean squared error, which basically for every prediction that you get for y measures the difference with the original value you have. So we assume we have observations for both x and y here, and we basically try to fit a linear function. Okay, so is y a deterministic function of x? Yes? Which y is a deterministic function of x? Y hat, right. But that's not our real y, right? But the y in our model is a deterministic function of x. Okay. So something to keep in mind, because I'll get back to that later, is that here we have something that does not have a deterministic relation with x, but in our model, it has. So we're making, again, an assumption here. Okay, so if we do this, is this machine learning? We've been doing this way before there was such a thing as machine learning. It was called statistics. Well, okay, so according to the definition, is this machine learning? Well, you can have a good look at that yourself, because there's a second notebook that is available for you. Basically, you can go through this and have some data and look if you have more data, does the model improve? So does it improve according to your performance measure once you have more data? And this is just a simple notebook you can run through. So let's say I'll just give you 5 minutes just to give you a feel of it. And the steps you should go through are in there, and hopefully they're clear enough. But if they're not, there are TAs here that can help you with it. Okay, so hopefully you have had a chance to go a bit through the notebook. The question is really ML? I already received an answer before we started. So I guess that's based upon experience. According to the definition, it should be machine learning. Because if you have more data, then according to your performance measure, you get better at predicting y, which was the task. Was there anything probabilistic in this?
Technically not, but if you're very, very stupid
Okay, so yeah, if you look at the notebook, basically the only thing where you did see distributions was for generating the data. And here, this is a deterministic function you're trying to fit in there. And then, of course, you say, well, there is not a perfect fit, so you know there's some uncertainty there, but it's not captured in this expression, right? So you won't see it in this expression. Later on, we'll see how we can get a more probabilistic flavor to this. Okay, so, well, the linear regression model, we could say it does capture machine learning, but the model itself is not a probabilistic model. But we can approach it from a probabilistic point of view, as I said, but I'll give you an example of that later on. Okay, so what is a probabilistic model and how can we learn it from data? So here I'm going to look at basically the simplest model that is possible, just to make sure we don't overload you with too much symbols and math. So I'm just assuming there's one random variable which has a probability distribution or a mass function or density function, depending on whether it's discrete or continuous. This function is f, and I have one parameter. So as I said, right, a Gaussian already has two, so this is even simpler than a Gaussian distribution. I have one parameter. And what we want, so we assume that the general model is known, right? So I have some hypothesized theoretical probability model, but I don't know what the parameters are, or in this case, what my single parameter is. So the fact that that is unknown, this is a notation we use. So if it's f of x, our random variable x, and this model has some parameter theta, and so we do x semicolon theta or x given theta. And our goal now, the learning problem, is to estimate the parameter. So we have the data, so we have this hypothesized model, and using the data that we have, we try to uncover what the hidden parameter was. So what do we have? How can we do that? Well, as I said, we have data. So suppose I have a sample with n observations, which I know or assume to be drawn from this hypothesized model with this underlying parameter. And then we define the likelihood function as basically the probabilistic model with the unknown parameter. And we write it like this because it's a function of the parameter. So my model will be different every time I pick another value or set of values for my parameters. I will get a different probabilistic model. So that notation just emphasizes that it's a function of my parameter. And if I assume that all those samples from that one single variable are all IID, then I can just multiply the probabilities of the single observations given the parameter, and I get this product. So I just assume now that the density function or the mass function, again, depending on whether I'm looking at discrete or continuous variables, is a function of the parameter. So let's look at a more concrete example. So I'm just flipping a coin. And suppose I just want to know if it's a fair coin. Right? So I don't know what the probability of heads is. That's going to be my parameter. So here I have a simple model, one random variable, one parameter. Now, there are 2 points of view that I can consider, either the frequentistic view or the Bayesian view. And I'll try to argue why perhaps the Bayesian view can be better. So from a frequentistic view, I could say, okay, this parameter, I've got this coin. I may not know what the probability of heads is, but it's a fixed value. It's a fixed quantity, right? So the only way to know what the value of that parameter is to flip the coin a dozen times, an infinite number of times actually, and then I just count how often do I see heads and how often do I see tails, and then I know what the value of the parameter is. Right, so it's a probability is a relative frequency in the long run. So, okay, I could say, okay, let's model this. So, as a probabilistic graphical model. So I've got this random variable, and I did all these coin tosses because I have to gather data first, because otherwise I cannot determine relative frequencies. So I flipped it 50 times, and I now have this sequence of heads and tails, and now I can estimate the probability of heads, because I've seen heads 15 times, so the probability is 15 over 50. Okay. So what's the underlying theoretical model I'm using here? Well, it's coin flips. So I just take the binomial distribution. I flipped 50 times. I have this parameter p, which is the probability of heads. And so I can write the likelihood function, right, as a function of p. So I just have the formula here. X is the number of heads that I see in my 50 flips. And I know, usually I would know what p is if I apply these kind of functions, but now I don't. But I can, for example, plot it for a number of values, different values. So what I see here, for example, if I find 10 heads in those 50 flips, then this function here gives me the likelihood, so the probability of finding those 10 flips for different values of the parameter. So this already gives you an idea of the uncertainty or the dependency on the value of the parameter right here. And here you see the one, if I find 25 heads in 50 flips, it looks like this. And that is not very surprising, right? Because here you see that the most likely value is at a probability of 0.5. So indeed, if the probability of heads is 0.5, you would expect to find 25 heads in 50 flips. Okay, so the likelihood function is a tool that already gives you some insight into the uncertainty that is here. If we look at a Bayesian approach, and why is this interesting? Well, the frequentist approach, as I said, I need trials. So before I can say anything, I need to have seen a number of outcomes of coin flips. So I cannot make any predictions of things I've never seen or I've seen only a few times. And for a lot of applications in AI, that would be very inconvenient. So we basically also want to do things we've never seen before. We want to make predictions of things we've never seen and use all the information we have for that. So if we look at a Bayesian approach, we can basically start from the very first, without any data even, making predictions. And that is because if we assume this model, and I have this parameter, so my probability of heads, I'm just going to model it as a random variable. And note that I'm modeling it, so I'm not assuming it is a random variable, I'm modeling it. So the frequentist says, okay, this is ridiculous, this is a fixed quantity, not a random variable. And I say, no, you're right. It is not a random variable, but I don't know what the value is. So there's uncertainty there. So I'm going to model it as a random variable because I want to find out more about what this fixed quantity is. I have no clue. I'm going to model it as a random variable. So that means I can include information while I am getting some observations, but also prior to getting observations. And that's where the word prior is now used for the parameters. So prior to observing any data, I can put information about the parameter in my model. And using this Bayesian approach, it gives me a whole tool set that I can use. I can use Bayes' rule, right? Like we also did in the Bayesian network to basically reason against the direction of the arc. I have a prior information. I can combine that with the likelihood function that we just saw. And that means that I can compute a posterior distribution. So that means I can update my parameter if I see information. And looking at this way, so I have a prior, I see evidence, I see observations, I compute the posterior over my parameter and take that as a new prior, and that way I update the value of the parameter by predicting its value every time I get a new observation. And that means I'm just doing inference, like I did in the Monty Hall problem, except now I have a parameter which I could say it's not as such a domain variable. It's a variable that represents the parameter of my distribution, but I can treat it in the same way. So I could basically use a Bayesian network to represent this idea of Bayesian learning, where I have my variable x here, which I do have observations about. I'm assuming it comes from some hypothesized model with parameter x, and I'm just putting parameter x there as a random variable, which is hidden because I cannot observe it directly. That's why in the colors you now see a difference. So the gray ones are the ones that are observable. The white ones are the ones that we cannot see. All the random variables are in the circles, and there could be some other fixed quantities that we put outside without a circle. So whatever has a circle, we model as a random variable. So here the parameter is modeled as a random variable. And I can put a prior distribution on it. And every time I see x, I use Bayes' rule, basically, and compute a posterior. And that way update my parameter. Okay. So let's go through some terminology here. So as I warned you about, I'll be using prior and posterior in a more restricted manner than before. So now if I talk about the prior distribution, I mean the prior on the parameter. I'm using pi here to represent that. If I talk about the joint distribution, it's the joint on both, let's say, the domain variables and the random variables that represent the parameters. And this joint distribution is the product of the likelihood function and the prior of the parameters. And then when I talk about the posterior during learning, I'm interested in the posterior over the parameters. So that's pi of theta given x. Once I get an observation, I update the prior by computing its posterior, which is just the joint divided by basically the probability of the observation. So that means from the joint, I sum out the uncertainty in the prior. Basically, I sum out the prior and get rid of the uncertainty I have there. Okay, so these are the things we'll be looking at. We have a prior distribution over our parameters, and from the joint distribution, we can compute a posterior over the parameters. So again, let's look at the coin flip again. But now instead of first having to do 50 flips, I can just look at each flip at a time. So again, let's assume I have n flips here, and I've modeled so every variable here is a single coin flip. All of these axes. They all have the same underlying parameter, the probability of heads. And I'm assuming here, well, let's just make an assumption. The probability of head is a uniform distribution. continuous because the probability can be between 0 and 1 anywhere. I have no clue. So that means the prior is going to be 1. And you could say, well, why don't start with half? Right? Why not assume it's a fair coin and just start with a half? Well, so let's just start with 1. We're way off from half. Let's just see what happens. Right? Okay. So our likelihood, that is just a distribution here we're hypothesizing. So we've got a Renooij distribution here, and our parameter, assume uniform prior. Of course, this still depends on p because we don't know p. So we can combine the likelihood and the prior and get the posterior. Right, so we have the combination of the likelihood and the prior in the joint, which is in the numerator. And in the denominator, we have the same, where we sum out or integrate out the uncertainty in the parameters. So our likelihood function is given here. The prior is 1, so that's why you don't see it. And then in the denominator, we have the same, but we have to integral from 0 to 1. And that could be a problem. So how do we determine that? And let's say the only reason for why you would want to determine that is if you want to keep doing things exact, right? So if you start saying, okay, I'll just approximate it, that's fine, but that means you're doing approximate inference from then on. So let's say I want to do it exact. Well, one way to do is just to be smart and see if this resembles something you know how to handle. Yeah.
Technically, you can rewrite the lower part as the prior over x, and then you can just intervene for observation.
Okay, so you could say, well, we don't always need this because this is basically proportionate to the joint.
Yeah, you can also say that the integral over f of p times likelihood p should be nothing else than
The f of x, yeah. Yeah, of all x. Yeah. Which parameter? So we're working with a model where we that needs a parameter that we don't have yet. So we're trying to learn that parameter. So we have to sum out all the basically to sum out the uncertainty we now have, and we put in the prior. But sometimes you don't need to compute this at all. It depends on what you need, and I'll give you some examples of that later on too. But if we want to be exact, we need to compute this expression. So what you could do is try to see some pattern. And the pattern here is that what we had resembles the beta distribution, except it's missing something, right? It's missing the gamma part there. So that is the gamma function, not the gamma distribution. So the gamma function of n is n minus 1 factorial. So this is just the left part with all the gammas is just a number. And we have something that resembles the right part of the expression there, and of course we know that the integral should be 1. So what we have here, well, that was the expression I had, so p to the number of heads I've seen, and 1 minus p to the number of tails that I saw. I'm missing the whole gamma part, so I'm just adding that in. I multiply by that part and then divide it out again. So I'm just multiplying by 1. And because this is a constant with respect to the parameter, I can just move it in front of the integral sign. And that means that here, I just have an expression of the beta distribution and I know that the area under which should be 1. So this whole thing reduces to 1. And I'm just left with basically the part I had to add in to make it match the beta distribution. Okay, so this was the denominator of our expression. So if I plug that back into our original formula, I have to switch this, right? So that's what we see here. So this is, in the end, what we get. This is the part that corresponds to the denominator. This is still the numerator. And this whole expression corresponds to a beta distribution with these 2 parameters. So we now have a nice expression for the posterior distribution of our parameter, given the observations, the n observations we have seen up till now. And this works sometimes. But we can basically characterize what kind of models we need to choose to be able to do this. And that's where we get the conjugate priors and likelihoods. And probably you've heard these terms before, and perhaps you didn't really understand what they meant. But we say that a prior and a likelihood are called a conjugate if the prior and the posterior that you compute from the combination of the likelihood and the prior are from the same family. So what we just saw is if you take the binomial Renooij with the beta prior, you get a beta posterior. And it gives you exactly the parameters that you need here. And there are more combinations that you see here. So you have a Poisson distribution with a gamma distribution, not the gamma function, exponential distribution, normal distribution if you have only one of the 2 parameters that you want to learn. So these combinations you can exploit to do the exact computation of the posteriors.
Sometimes in the probabilistic text, when you read this maximum in posterior limiter, sometimes they say that, okay, the marginal is just a normalizing factor and we don't consider. And sometimes we are so obsessed with like calculating the marginal that nothing can move forward. When is the case that the marginal is so important? When is the case it is not that important, just
Well, I think I get, well, maybe not telling you when exactly is the case that is so important, but I'll just get back to a number of options you have later on. And because, yeah, you don't always have to do that. It's basically if you want to keep doing everything exact and keep it Bayesian in the sense that you keep distributions for everything all the time, then you do it this way. If you are fine with point estimates at some stage, then you don't have to do it this way. So it is how Bayesian do you want to be? Maybe that's the best answer.
regarding like the sampling method that you mentioned earlier in the slide, there we are not, there we don't care about the marginal, or do we care about the marginal?
Well, there you're not doing the full Bayesian approach. So that is basically the difference. Maybe in a couple of slides that will be a bit more clear, hopefully. It depends on the approach you're taking. So what I'm now talking about is a full Bayesian approach. So basically I'm keeping distributions over everything. So this was the learning part. So we assume a prior, we update it with data by computing posteriors, and we just repeat that with all the data we get. And then, of course, that was the learning part, then you still have in the probabilistic cycle, modeling cycle, you have the validation and the use. So doing the things that we originally did in the Bayesian network and in the Monty Hall problem, where we said, okay, you can compute a prior over one of the variables in your model, you can compute a posterior condition on things you see. If we do the Bayesian modeling and inference and learning stuff, usually these are called the predictive distributions. So now you're going to make a prediction. You're not the parameter learning, but you're doing the prediction. And then we typically call it the prior predictive distribution and the posterior predictive distribution, or just predictive distribution. But you're doing basically the things we've seen before. So if you look at the prior predictive distribution of X, so this is your random variable from your domain and not your parameter. So you just look at the joint, and again, you sum out the uncertainty you still have. So you're still representing a distribution of your parameters, right? So you still have uncertainty there, and you just sum that out, marginalize that out. And you can also predict what basically your next observation is going to be given the observations you've seen. And you can also use this to generate data, right? So this also gives you a distribution over the next data point, or a different data point given data that you've seen. So the probability of the next observation given the observation that you've seen is, well, you condition on the parameters, and given the parameters that were learned on the data that you have seen, your new observation will be independent of all the previous observations. So you can drop the X right here. You see it's no longer here. And here, you have the probability of the parameter conditioned on the observations you've seen. So that is just a posterior over your parameters that you have computed based upon the observations that you've seen. So the posterior predictive distribution, given the observations you have seen now, with which you can predict the next observation, you can compute it using this formula, where you see the posterior over your parameters, and here, this of course is just the f of x. Now it happens to be the m plus first x, but that doesn't matter, right? So we can also cast these two into our coin toss example. So we have the prior predictive distribution, which we saw before, and what we computed before. And the nice thing is, so that was just the gamma functions part left. And the nice thing is that you end up with a half. And remember, we started with 1. And you get, well, if it is indeed a fair coin. So even though you could have said, okay, let's just assume I have some domain knowledge that fair coins have a probability of heads of a half. I could have started with that, but it doesn't matter. Even if I start, well, way off, if I have enough data, I will get to the right prior. And for the posterior distribution, well, we can do a similar thing. So we have the probability here. This is just the f of x, given our parameter p. This was the expression, the posterior over our parameters that we put in there. And we do the same sort of, we can do the same sort of tricks to recognize the pattern of a beta distribution in here. And that gives us these additional gamma parts right here. So you can basically just analytically solve this whole thing. Okay. As I said, this works if you can use all these nice properties of the conjugate distributions. And the way we did this, so keeping distributions, basically using distributions all the time, keeping at the level of the distributions, doing everything exact as long as we can. This is what we call the full Bayesian approach. If you don't want to or can't do it that way, then often what you can, what is enough to use is either the map estimator, which is the maximum a posteriori estimator, or the maximum likelihood estimate. And probably you've either seen one or both of them in papers you've been reading. So this is just to give you an idea of what the difference between all these is and how they are different from the fully Bayesian approach. Well, if you look at the denominator of your posterior distribution, as I said, you don't always need it, because if I just want to optimize the parameter, find the one with the best value that maximizes the function, then what I can do is observe that I can just maximize the one in the joint. Right, so the posterior, I'm dividing the joint basically by the probability of x. The probability of x no longer depends on my parameter. This is what you said as well. And therefore, it is proportionate to the joint. So if I want to optimize basically the fraction, I can optimize the numerator, which is the joint, so the likelihood times the prior. And I can take the log of that. That simplifies things more. So that's when I get the map estimator. So basically recognizing, okay, the posterior is proportionate to the joint, I'll just optimize the joint. Find the parameters that optimize the joint. And that means I get a number, right? I no longer have a distribution over my parameters. You could even drop the prior. If you drop the prior, then you're optimizing this one. Just a joint, just a likelihood, sorry. And that's the maximum likelihood estimator. And you see that the relation between the three is difference between fully Bayesian, you're using all you just keep working with distributions. If you don't want to compute the denominator, either because you don't want to or you can't, you can go for a map estimator. And if you forget about the prior and basically lose everything that had to do with a Bayesian approach, you're at the maximum likelihood estimator. And basically, this is what you'll find if you use a frequentistic approach. Right? This is just looking at what is the most likely value. And that's, then you're here. Okay, so when are these two, the map and the MLE, the same?
I think in map we get a distribution over the latent parameters or the parameters higher in the hierarchy. And in this MLE we would get the point estimate of the latent parameter that maximizes the evidence that we have observed.
Yes.
I think that's the major difference, because then in the map estimate you could sample another latent parameter from the posterior that you would get, and then you would have another you would have a little different evidence probability of observing that evidence what you observe. So every time you sample a different from the posterior parameter.
Yeah, but if you look at the formulas here, you're looking at exactly the same evidence and you're exactly the same parameter, right? If I understand you correctly, you're using different latent variables, or assuming different latent variables for the two approaches.
In the sense that, suppose for this, the coin flip, we assume that the coin is fair or not, and the fairness of the coin is modeled by another
But here I'm still assuming basically the structure is the same. But, and the variables are also the same.
I mean, the values would be different.
The value could be different. Yeah, the value would be different, well, depending on the choice of prior here. Because in fact, I take a uniform prior here, which gives you exactly the same number for every value of the parameter. Then of course it's not doing anything. So then these would give you the same estimate. And also if you have lots and lots and lots of data, then your original, because this is the original value of your prior, not the updated one. So if you have enough data, you will have already updated your parameters according to the data, and the prior will not be that will not have that much of an effect anymore. So if you have a lot of data, then there's not much difference between these two. So being completely Bayesian or staying a bit Bayesian by using the map estimate works best, or you will find the difference, the biggest difference, if you have little data. So that's also why often they say if you don't have that much data, it's better to use a Bayesian approach. And it really is different to use a Bayesian approach. Okay, so let's go through some examples. We have of course seen the coin toss. Some parameter, the probability of heads. So, well, x is a random variable. If we want to take the Bayesian approach, the parameter is a random variable. Are there any other quantities? Oh, sorry. Well, I'll just give you the picture here. So I could start like this, right? So I have these coin flips. I have a parameter, probability of heads, and I also have the n here, which is the number of flips I did when I looked back in the first case. And we said, okay, if we take a Bayesian approach to this, we'll just model our parameter as a random variable. So which one is that? Only theta or also n? N not, right? N is just a number of flips, so that's a fixed. That's really a fixed quantity. It's not something I want to learn, so it doesn't make sense to turn that into a random variable. So I can turn my parameter, the probability of heads, into a random variable, and that could itself also have its own parameters, right? So possibly because, as you said, it could be that the coin is indeed not fair. It could have a bias towards tails, and I could represent that also as an underlying unknown variable, right? I can say, okay, there is a bias towards tails. I cannot see that. I cannot observe that directly, but I can model it explicitly. So I just add another variable, and then I have to think about where to add it directly. So is it, like I suggest here, just influencing the probability of heads, or is it also directly affecting my outcomes? Here I assume it doesn't, only through the probability of heads. And it could have its own parameter, of course. For example, telling what the probability of tails is. So I could say the variable t only models that there is a bias towards tails, and it can have its own parameter telling us what the actual bias towards tails is. And I can also get two coin flips, both having their own probability of heads, and for both I could indicate that it has a bias or not towards tails, and if it has, it could have the same bias. So I could extend that any way I want. Another a simple example is a naive Bayes network. And this is basically what is underlying naive Bayes classifiers. So you don't always see this represented as a probabilistic graphical model, but it's a very simple one which has this structure. And often what you would be predicting here is y, a class variable that's typically discrete or categorical, and the features are the x1 to xk. So these are really typically different random variables, so not k coin flips, for example, but k different features. And you can use Bayes' rule basically to predict y given all your observations, and these are typically learned from, so it's a supervised model, so you know the x's and the y's to learn them from, and you can use it to predict. So, as I said, well, this were a model with k different features, so that's different from one outcome of a coin and you repeatedly flip the coin. But if you do have these repeated observations for the same random variable, you can model them explicitly like we did before, but you can also imagine that your graphs will blow up at some stage if you do this. So you will often find a plate notation like this, to basically just summarize what's going on and to get rid of all these repeated structures. So what this describes is, okay, we've got this underlying parameter theta, and here I have n different observations for my random variable x. So just give it an index of how often it occurs. And using that, you can in fact try to model quite complex processes. So this is getting back to the linear regression model. So we said the way we captured it, there was basically y hat was a deterministic function of x. And we said, well, that is a way to approximate, but our true y, of course, is not deterministic. So here we can try to model that by saying, okay, I've got a random variable y right here. And again, let's say I have n observations. And the random variable y is conditioned on my observations x and some weight vector. So it's a weighted combination. And I could say, well, I could also say w, the weight vector, is taken from some distribution with its own parameters. So here we see that they have normal distributions. I have a noise parameter there that I can include, which can again have its own parameter. And you can just build a model the way you would like it to work. And you see, okay, for every observation, I have some noise, so that is the part that is repeated, and the weight vector is the same regardless of the x I see and the y I predict. So this is in an unfolded representation. This is using the plate notation. And you see now y is a random variable. Okay. What we saw is if we have a Bayesian network, for example, then we can compute any probability we want from that because we have a definition of the joint distribution. If we look at the linear regression model here, notice that I turned y into a random variable, but I didn't turn x into a random variable. So that means my joint distribution doesn't include x. So I cannot use it to predict x. So I cannot use this to generate more observations. If I want to do that, then x needs to be a random variable too. So most often, what we learn when we learn these probabilistic models is we learn a joint distribution, and that means we can use it to compute any probability we want and also therefore to generate data from, right? We don't have observations and predict some unknown variable from that, we can also do it the other way around and just predict new observations. So, and that's why we also, these are called generative models. And typically, naive Bayes and Bayesian networks, the models we've seen, are such models. And if you only directly estimate the distribution of over what you want to predict given what you see, then this is called a discriminative model, which is basically optimizing for the variable that you want to predict. It's not optimizing the joint. Well, they both have their benefits and their drawbacks. So typical examples of discriminative models are logistic regression, also neural nets. And the benefit is that they have a lower asymptotic error if you have enough data. But it takes more time to reach that. So you need more data to get at a better result. If you look at the generative models, the error may be a bit higher, but you reach it more quickly. So you can also already do good things with less data. And you can generate data. So just go through a couple of examples of well-known probabilistic models, and also trying to capture those using the plate notation. So one of these is a mixture of Gaussians. And that's a model that is often used for clustering. So that's basically unsupervised classification. And what we assume here, we have all these colored data points, and we assume that they are from different clusters. And those different clusters are represented by these normal distributions right here. And, well, we've drawn the image, but we don't really know what these clusters are, right? So I have my observations. So these are the colored points, xi. I'm assuming they come from k different clusters, so I have to make that choice what that k is. And these are Gaussians that are generating, I hypothesize that these are Gaussians that are generating that data. And the parameters are the frequencies. So basically you could say there's a probability of 0.3 that the red cluster is generating the data, and cluster 2 has a probability of 0.5, and the last one has a probability of 0.2. So these sum to 1. So all these data points are with some probability generated from one of these distributions. And so all these k clusters, they are normal distributions. They have their own mean and standard deviation. And every data point comes from one of these clusters. So the z there indicates which one. So it's one of these k's, and the probability is determined by the frequency theta. So this is the plate notation that allows you to basically represent this mixture of Gaussian model. And it tells you, so you can read what the dependencies are, what are all the factors that are playing a role here. Well, what you have is, so these two, I made another step because this way all the the parameters were still fixed quantities, and I can turn it into more Bayesian by making those variables as well, and they can then again have their own fixed quantities. But you need these are basically characteristics of the clusters, and then so you know that there is a number of data points from every cluster, And basically the mu and the sigma will tell you what the probability is that several data points are generated by these different clusters. But if you look at an individual data point, you know it's generated by one of the clusters. You just don't know which one. And that is basically what the Z is indicated. And if you know which cluster, then you also know what the mean and variance of that cluster is. But you need the Z to indicate, it's basically an indicator of which cluster this single data point is from. Does that answer your question? Okay, thank you.
Why is theta not found in the cluster if the plane location is equal to mu and sigma? Because theta is also theta 1 and theta k, and mu, j, and sigma j are also from 1 to k.
Because the theta tells the frequency with which you have the different clusters. So that's more global. So it's a probability that basically that cluster is used for any point. And that's why it's outside.
How does the learning happen for this GMM?
How does the learning happen for?
Like, if you just have the data, so how do you find the Gaussian function? How do you find the mu and the sigma and theta?
Basically the way we discussed. So what you do, so you don't learn the structure. So you define that this is the model that you're interested in. And in this case, I say, okay, theta and mu and sigma are my unknown parameters. I'm getting these. And then just basically employ the procedures we just discussed. So anytime I have an observation, I know what the relation is on these arcs, say. So I start with priors and compute posteriors for them. So it's basically the process we just discussed. It doesn't matter what the meaning of the parameters is.
We find the posterior or the maximum a posterior or maximum likelihood for theta, mu and j together, or like how, so everything we just find together a posterior.
Well, in this case, it's this one is conditional on, well, you can see them there. So you can, if you do the inference, yeah, this is hard to explain without all the formulas, looking at the formulas. Because we, of course, looked at a very simple example where there's only one parameter. But the idea is exactly the same. So for every parameter, you can compute a posterior given the observation that you do. Okay, let me see. Very quickly go through this one just to show another example of a factor analysis model where you can think about, okay, you have, for example, a questionnaire where you've been asking a lot of questions, you get a number of answers, and the idea is that all these answers are basically, can be represented by some underlying factors, which you don't know. So the idea is to predict from the observations you have. So now you have a high dimensional observation, x1 through xm, and a lower dimensional list of factors that more or less generated those observations. And you don't know these. So now we have hidden variables, which you not necessarily are parameters of your probabilistic models, but these are true variables, you just don't know them. And you can do exactly the same. It doesn't matter if the latent variable or the hidden variable is just a domain variable that you haven't seen or is a parameter. The thing works the same. So I'm not going to go into much details here. I just wanted to say a last thing about inference. As I said, we were focusing on exact inference. which can already, even especially for discrete models, become very complex if the models get too large. It's exponential. It depends also on to what extent you can move those summations into the product in the variable elimination, if you can find the best way to do that. And that is called the elimination order. And as long as we have closed form solutions to the product of such local models and the summation or the integrals, computing the integrals to the marginalization, then you can do that. And otherwise, you have to resort to approximate inference. So just two that I wanted to mention, and not go into any details, just to mention them. I mentioned the Monte Carlo techniques as sampling. I mentioned that there are deterministic approaches like the variational methods that you will be seeing more. And just very high level, what are the benefits and drawbacks of these approaches? MCMC, for example, is accurate as long as you have enough samples. So then you're basically guaranteed that your approximation will be the true values. But the drawback is that doing the sampling itself is computationally demanding. If you go to the deterministic approaches, what you first do is you approximate your model to something that is more feasible. But that means you're always off, right? You never get the right answer. But at least you can then do all the inference, and it scales very well. So again, depending on how important it is in your domain to have exact answers, or is it okay to have approximations? And do the approximations need to be accurate sometimes? And do you have the computational power to get enough samples? Those are the kind of things you have to take into account to decide what to do. So it's very much dependent on your domain and what you want to do with it. And you cannot really say anything more than, okay, these are the benefits and drawbacks of the different approaches, and you see what is important to your domain. So, to conclude, if we look at probabilistic models or probabilistic graphical models, I hope to have convinced you that lots of probabilistic models, you can represent them using these graphical structures that give you nice insights into how your domain is, or how your model is structured. And also, I hope to have shown you that inference and learning in the Bayesian context is actually basically the same thing. You're doing the same kind of computations, except that the goal is different. Either you're just computing probabilities from a complete model, or you're trying to learn the parameters or the latent variables you have in your model. If scalability is important, well, you have to resort to approximate inference. And the most important thing is of these kind of models that they're to some extent interpretable. Thank you very much, and enjoy the rest of your week.